Welcome back, Calculus 2 students. The goal of week 2 is to cover Chapter 6, Applications of Integration. Chapter 6 consists of 3 important sections and a couple of unimportant ones. Number 1, area. Number 2, volume. Number 3, some more volumes. Those 3 are important. 4 and 5 are not, particularly considering that this university has no engineering program. But before that, let's review Calculus 1 material a little bit. After all, the definite integral concept was closely related to area. The definite integral we talked about in Calculus 1 was visualized by a signed area, kind of like this. Blue area, positive, minus red area, negative. If we be a little bit careful and divide this interval into 2 pieces, right around here where my mouse is, around 1.2 something, maybe 1.3 something, then we're going to be able to separate this integral into the red part and the blue part. And by taking the absolute values of those integrals and then adding them up, I'm going to be able to calculate the absolute area captured by the graph of the function and the x-axis. Excuse me. In fact, we have already done this kind of problem in Calculus 1, kind of like this, and kind of like that. Let's talk about the first problem only, leaving the second problem, which is a little bit harder, as an exercise to the students. How do we find out the area? Do we simply take the integral from -1 to +1? If you do, you're going to get nothing. Literally nothing, because you're going to get integral 0. And how can you get an area of the shaded region 0? That's impossible. That's because this is an odd function. Consequently, the positive part over here on the right hand side and the negative part right here on the left hand side will cancel each other out. So how do we handle this difficulty? Number 1 is to separate this integral into 2 pieces. Calculate the integral from -1 to 0 and calculate the integral from 0 to 1 separately, and get the absolute values and add them together. That's the standard way that we are going to employ in Calculus 2. But in this particular case, let's rely upon the symmetry, because right hand side and left hand side are the same because of the symmetry. So all I have to do is calculate this integral from 0 to 1 and double it, kind of like that. How do you do this integral? It's a substitution. U is the inside, calculate du dx, calculate dx, and then substitute everything back in. When x equals to 0, u is 1 minus 0 squared. When x equals to 1, u is 1 minus 1 squared. Plugging everything in, we get this, and then this x and that x will cancel each other out, and this negative sign and this flipping of integral from 1 to 0 to 0 to 1 will cancel each other out. Consequently, we have this kind of integral down here. Applying the power rule and then the fundamental theorem of calculus, we're going to get the final answer. Alright, we have done this kind of problems. Area captured by the graph and the x-axis. What we haven't done in Calculus 1 level is the area between curves, kind of like these. This example may be a bit too tough, so let's go back to our textbook and let's talk about some easy examples first. Kind of like this one. Area between the regions where there is no intertwining zone, so we don't have to consider additional crossing points. All I have to do is consider this part, the S shaded part, and let us do that by forming appropriate Riemann sum. We can do it like this. For given subinterval, we have subinterval length delta x, and a y-coordinate value is given by the difference of the function values, f minus g. And add them all together and you get a Riemann sum like this, which can be represented as Riemann sum like that, and take the limit as n goes to infinity, or equivalently speaking, the partition size delta x going down to 0, we're going to get a definite integral like this. Here, please note that f is greater than or equal to g. F is an upper function, g is a lower function. What if you switch f and g? In that case, you're going to get negative value as an area, don't panic. All you have to do is just flip it over and then you're going to get the area. And that works as long as there is no intertwining zone. If there is, that's going to be a bit bigger problem. But let's postpone that and let's go back to our notebook and then do an elementary problem. Right here, problem A. The upper function is given as exponential function. The lower function is given as a quadratic function, and the starting and ending point of the interval are explicitly given. You can't get any easier than that. Here's the graph, and excuse me, let's make it a little bit more explicit. Okay, that looks a little bit better. The thick blue graph is the upper function, y equals to e to the x. The thick red graph is the parabola, y equals to x squared minus 1. As you can see, blue is the upper function, red is the lower function, and integrated from -1 to 1, upper function minus lower function, we're going to get the area. And that's this computation right over here. Computation step is easy. I'm going to leave that to students. Okay. What about a little bit more complicated example like that? Do we simply take the integral from the starting point and to the ending points? That's a bad idea. If you do that, you're going to get something like this. In the blue region here in the left hand side, you get positive number. In red region down here, you're going to get a negative answer. And blue region again, you have positive. Add them all up. You're going to get certain value, which is not an area. That's going to be assigned area, the definite integral, not the answer you're looking for. One way to handle that is to make all those regions positive by taking the absolute value and make everything positive there. An elegant notation, yes, but totally useless. Because what integral formula do you remember with absolute value? Nothing. A logarithmic function with absolute value, but that absolute value took place after the integration, not before. So this method or this expression looks good, but is totally useless. So how do you actually handle that? You do it by finding out the crossing points. Oh, before moving on to crossing points, let me show you another type of example. This time when the region is given when the curves are given as a function of y and regions are given kind of like these. Is it okay to do that? Yes, it's okay because we are talking about the area, not functions. So x equals f of y, that's perfectly okay. Again, we have regions like that, and then it's going to be necessary that we find appropriate crossing points and then divide the integrals into several separate pieces and take the antiderivative separately. In order to do that, we have to find out appropriate crossing points like these. So if you set two functions f of x and g of x equal and solve for x, then you're going to get the x coordinates of these crossing points, these red points. These crossing points divide the original interval into several pieces and calculate the integral separately and use appropriate signs, then you'll be able to calculate the positive areas of each region precisely, and then you can add them up. You can do the same thing with respect to y. Exactly how? Let's look at an example. Let's look at example C, and this is actually a preparation. Here we have a function, another function, but no starting and ending points are explicitly given like previous problem. How do we handle those? Let's look at the graph first, and lucky, we don't have intertwining zones, so we don't have to consider additional crossing points. Here's one and there's another, and all you have to do is find out these two and set up an integral, and then we are good to go. How do we do that? Well, y squared minus 4y and 2y minus y squared must be the same, so we set up a quadratic equation like that. Solving it is easy. It's just intermediate algebra, maybe elementary algebra. move all of them into one side, factor it, and then we have the answer. So we have an integral from 0 to 3, upper function minus the lower function, and integrate it, use fundamental theorem, and we have an answer. What if we screw up and then switch upper function and lower function, kind of like that? And then you do all kind of computation afterwards. If you do that and do it right, you're going to get a negative answer. At this moment, you will know, even if you made a mistake early on. So what you do is change this to positive, and then change this integral to appropriate sign, and then change the intermediate steps accordingly, and then you're going to be okay. Of course, if you rewrite everything like this, it's going to be even more desirable. Okay, let's move on to the main example. How about this one? Let's look at the graph, and then this is going to be a problem because we have additional crossing points down here and there, and consequently we have positive region, negative region, and positive regions. So if you integrate it from negative pi over 2 to 3 pi over 2, then you're not going to get correct answer. So first thing you have to do is to find out the crossing points and then separate this interval into 1, 2, 3 separate regions and then integrate them separately. How do you do that? Let's set up the trigonometric equation like that. Sine of x is equal to cosine of 2x. How do you do that? Let me remind you of the double angle formula for cosine. So we have sine of x is equal to 1 minus 2 sine squared. Consequently, we have a quadratic equation of a sine, and we can factor it, find out appropriate sine values, and then go back to your fundamental domain from negative pi over 2 to 3 pi over 2 and find out which x values correspond to those sine of x to the 1/2, sine of x equals to negative 1. Turns out pi over 6 and 5 pi over 6. So what we have an integral from negative pi over 2 to pi over 6, and pi over 6 to 5 pi over 6, and 5 pi over 6 to 3 pi over 2, kind of like that. Blue represent the blue region, and red represent the red region. Let us minimize this window and then show these two in the same viewing window. Do you see the color coding? Blue corresponds to this blue region, red corresponds to this red region, and blue corresponds to that blue region. The upper function for blue is cosine of 2x. You see that more wriggling. And upper function for this red region is sine function. We have just one wriggling here. Calculating these definite integral is easy. All you have to do is take the antiderivatives using the antiderivative rules and then use fundamental theorem of calculus. Plug in the top, plug in the bottom, subtract one from the other. I'm going to leave the rest to the students. Here is the computation through Mathematica, and then adding all those we get, well, 3 square root of 3, and that's going to be the final answer. By the way, you can check whether that is true by this absolute value computation if you have computer algebra system. But of course, this is when you have Mathematica or things like that with you. In general, this kind of thing is useless. This absolute value notation is pretty much useless. This is what you'll have to do. Find out the crossing points, set up separate integrals, and calculate them separately by calculating their antiderivative separately and applying the fundamental theorem separately. So much for the area problems, and the rest of the problems are left to the students. In the next segment of the videos, let's talk about volumes.